me first share the slides, you guys. Okay, so Shamira is here. How are you, Shamira?
Assalamualaikum, Doktor.
Waalaikumsalam warahmatullah. Okay, so I'm actually wanted to share the slides now. Where is it? Okay, so can you guys see the slides? I hope yes.
Yes. Yes.
Right, so last Tuesday is just a recap. We have learned about a few formula on calculating the corrosion rate, calculating the current density, and whatnot. I believe the most important formula that you guys need to remember is basically this one. Okay. So the mass loss using a Faraday's law is given as current multiplied with time multiplied with molecular weight over valency multiplied with Faraday's constant. M equals to ITM over NF. And you can also calculate corrosion rate, okay, which the unit will be in millimeters per year, MMPY, which is equals to M metal loss over area multiplied with time and density. That is also equals to current density multiplied with molecular weight over density multiplied with valency and Faraday's constant. Right. I think yesterday, Madi was asking me about the relation of this formula. Okay, corrosion rate R equals to MPY in MPY unit equals to 0.13 multiplied with corrosion current density multiplied with equivalent weight over density. Okay, you cannot actually relate these two formula. The reason why is because this formula, okay, is actually generated from a natural occurring process, which weight loss. You put a metal inside a solution and then you let it for some time to corrode. It occurs naturally. Meanwhile, this formula, 0.13, okay, as well as this one, 3.26, is actually when you use induced current methods. In this case, if you use potentiostat or anything that drive the current, okay, accelerate the current, then we cannot actually relate the current density produced from one method to another method, because it's not the same theoretically. So that is why we cannot, if let's say you got the current density from this formula and then you put into this formula and want to see the difference, you cannot actually get the same value. You cannot relate. But of course, if you want to compare this formula with this formula, that the corrosion rate using Math's laws, and the corrosion rate that use current density, and this one actually you can relate because it's actually from the same process, and what differs is just the formula. And of course, this one probably it can be linked. Right. I hope that probably if you have any problem on the corrosion current or density or the corrosion rate formula, please ask me. Quickly before your exam or your test. So any questions so far? Anything that you want to ask? Anything before we proceed with our lecture today? Is it okay to everyone?
Okay, Doctor.
Right.
Okay, Doctor.
So after we have calculated the corrosion rate, what is important is basically to classify them, whether this material will experience severe corrosion, mild corrosion, or less corrosion. That is why we have a classification of corrosion rate for different types of metal. For example, for carbon steel, you have a classification. If let's say the corrosion rate is less than 0.03 mmPy, then it means that the process of corrosion is very less. Then the material will actually be classified as excellent. It doesn't have any degradation. It doesn't have any corrosion attack. But if it is actually greater than 0.25, then you know that this actually indicating the carbon steel will experience a very poor condition. It experience severe corrosion and whatnot. So as I said, different metals will have different classification. This is basically based on ISO 9223, corrosivity classification. Okay, so this is basically for metals, iron, basically for steel. You have C1 until C5 classification. C1 means that the material doesn't experience much corrosion, very less corrosion or no corrosion at all. But if the category is C5, then you know that the corrosivity is considered to be very high, and this actually indicates that the metal experience a massive degradation. For carbon steel, zinc, copper, and aluminium, the classification is different. This is basically depending on the types of metal. So as you can see over here, for aluminium, even a slight change, normally just 0.01 or 0.001, it already classified as class 2, because aluminium, for your information, it is known to be a very reactive metal. Immediately, if you put aluminium in water or in acid, it will react spontaneously. Then, any slight difference in corrosion rate, meaning that the material will experience corrosion. So that is why the classification for aluminium, even at the slight or even at the low corrosion rate, is already been classified as higher number, okay, higher category. For copper, you will see it's slightly lower, okay, but for other things like zinc or others, it can be also classified for different category. So similar explanation in terms of corrosivity categories. For C1, only few corrosion attack, and then this one is basically where at the alpine areas, For C2, we can say that normally occurs at the urban area, rural area. C3, normally coastal area near to the marine side. C4 is for seashores, and then C5 is for seashores that have, or offshores that have a very, high attacks of tidal or others. Okay, factors that affecting corrosion. These are a few things that you need to understand. Of course, things that can affect materials corrosion is basically on materials properties. The composition of metals or materials will determine whether the metals or the alloy will be corroded or not. So for alloys, for example, if it is been doped with zinc, then you know that this material can easily corrode. Okay. Another thing will be on metallurgical factors. Okay. In pure metals, anode areas are grain boundaries or small micro heterogeneities. In alloys and metals with impurity, it is always related with chemical segregation, presence of multiple phases because both elements could be not homogenized, inclusion defects, and non-uniform stress. Other than that, it will be on the surface condition, because if the surface condition is not homogenized, it has a scratch, it has a formation of oxide phloem passive layer, then this can actually slow down the corrosion process. Okay. The surface condition that inhibits electrochemical reaction of metal with environment basically is due to the formation of uniform oxide phloem. Okay. If you have a passive layer, then this actually can create a barrier to separate the environment of metals to electrolyte or metals to environment. Another thing will be the phloem that is formed due to the gas absorbed. And another thing is also due to the surface effect. Right. Other than that, the factors that can affect materials corrosion is basically due to the environment. If we are working on a chemical natures with a strong acid, with a strong base, then of course, we have a higher tendency for corrosion to occur. Higher salts concentration like acids, neutral, and alkaline salts is also another concern. If you have like gases, like corrosive gas, H2S or others, this could be also dangerous for metals. Another thing will be on the operating condition. For example, the temperature, velocity, concentration, aeration, impurities, and others. Right. So basically, I give you this picture. This is actually like a pillar that is used to reinforce the jetty or the marine jetty. If you notice, I put a scale over here, 2, 4, 6, 8, and 10, where the region at 2 and 4 is normally having a severe corrosion compared to region 6 until 10. Anyone knows why this region having a severe corrosion as compared to the other region? Any suggestion? Atira, what do you think?
Maybe because of the depth of the sea.
The depth.
Yeah, because at different depth there will be like different temperature condition, different concentration, maybe.
Okay, all right. So I take that as one point. How about others? Mariam?
I have no idea, Doctor.
No idea. Okay, right. So basically, if you notice over here, okay, so I put the zone of exposure. The zone of exposure, you have HWL and LWL. What does it mean by HWL? Okay, so HWL means that high water level, okay, is and then you have a low water level. Where you can get high water level and low water level, this actually depend on the tide change. You know, tide, because at certain time, okay, the level of water is going to be low and sometimes it's going to be high. This we call it as tidal change. Okay, so because of the tidal change, for example, if it is a low tide, then you will see that this area will be exposed to the environment. It will be exposed to the air. It will be exposed to oxygen during low tide. And then during high tide, what happened is that this area will be covered again with water. In the same time, there's a wave. Okay, and wave actually can create a so-called like erosion effect. When you have like a combination of oxygen concentration exposure in dry condition, in the same time with erosion of high tide, then this actually can create corrosion, especially to this area. Okay, so I hope it's understood now. Temperature probably, yes, it's another concern, but in some countries, the temperature of water is going to be like consistent all the time. I mean, like if you go to four-season country, then probably the temperature would be, I mean, different at different months. But for some countries, especially like Malaysia, we always like having, I mean, like the same climate, and then the temperature of like water is going to be like not significant. So as a summary, we can actually see factors that affecting corrosion due to many things, due to the exposure to the chemicals, due to the external factors, environment, surface, and others. Okay, so same thing, is just to explain about corrosion and corrosion control, what actually affects degradation of materials. And I guess probably today we are going to learn about types of corrosion. So it is important for you guys to know what will be the types of corrosion. And of course, understanding each and every types will be essential in order to answer your exams. Because normally I will ask what would be the definition of each corrosion type. And then if you are able to explain with the the guide from like drawings or others, this actually can help you. Basically, types of corrosion can be categorized into three types, major types. Okay, so we can have like general corrosion. You can also have localized corrosion. And finally, we can have combined effect. Another effect that maybe types that we rarely discuss is microbiological corrosion. Okay. So what does it mean by general corrosion? General corrosion, it means that the corrosion occurs generally. It forms a homogeneous layer or homogeneous process. That's why you'll see that the surface will be like all corroded. This we can categorize it as general corrosion. Localized corrosion, in turn, it means that corrosion only occurs at the specific site. Okay. Meanwhile, combined effect, okay, basically it is a combination between mechanical plus electrochemical effect. Okay, so you have mechanical effect, like for example, erosion with corrosion. So this can be categorized as combined effect. And finally, microbial, it means that the corrosion basically happen with the help of bacteria. So some bacteria, microbes, okay, induce corrosion. Right? So we are going to look one by one for general corrosion. There's no specific or there's no subclusters. Localized corrosion, you have pitting corrosion, crevice corrosion, galvanic corrosion, intergranular, selective, and filiform. And for combined effect, you have a stress corrosion, corrosion fatigue, corrosion erosion, and fretting corrosion. Right. General corrosion, it means that you have a uniform attack, okay, in the form of electrochemical corrosion that occurs with equal intensity of the entire surface of the metals. So metal will be corroded uniformly over the surface. So this proceeds at approximately the same rate over the whole surface being corroded, and the extent can be measured as mass loss per unit area. Okay, so if you see this example, you can actually understand that these materials actually undergo equal intensity of corrosion attack. Localized corrosion, as I said, part of the structure will be corroded at considerably higher than the average rate. The categories of local corrosion are pitting corrosion, crevice corrosion, galvanic corrosion, intergranular corrosion, selective corrosion, and filiform corrosion. Okay, so the first one, pitting corrosion. How actually pitting corrosion can happen? Okay, so pitting corrosion can happen when you have a failure of passive layer. So if you understand stainless steel, okay, stainless steel, what makes stainless steel didn't corrode is because it has a passive layer. Passive layer of what? Chromium C oxide. Okay. All right. So this layer is quite resistive. It cannot actually easily penetrable or what. But if there's some failure in terms of like scratch or cracking, then it will provide cracks. Okay, so you have failure due to probably scratch or cracking. So what happens is after you have a failure of this layer, this actually can provide a gap. Okay? It can provide a gap for oxygen and water to penetrate. So what happens when oxygen and water penetrate to this gap? Of course, what will happen is basically it will form corrosion. So the types of corrosion that will form underneath the layer is basically on a pit size. Okay. The formation of small pits on the surface of metal or alloy is known as pitting corrosion. The corrosion effect is concentrated on localized area and lead to pitting. Downward propagation of small pits and holes are where the precipitating process layer fails. As I said, when you have a crack, then what happens is that oxygen and water can easily penetrate to this region and it will actually create corrosion. And the corrosion actually forms like a pit and it is a downward propagation. Okay. Right. So this is actually the keywords. You have a precipitating layer fails, okay, downward propagation and formation of small pits. This is basically the keywords if you want to define pitting corrosion. And if you wanted to answer in every exams, Probably you can write this with these keywords, and of course, you will need to like at least draw some structures to explain this actually pitting corrosion. Examples that you can see are if it forms like a hole like this actually means that there is a pitting corrosion. Right, so pitting corrosion forms a passive alloys like stainless steel when the thin oxide layer is broken and does not immediately repassivated. Pits can become wide and shallow, okay, or may rapidly perforate the metals. The most often attack that take place at point where the passive layer might be weakened, okay, and if you have a surface defect, for example, a scratch or what, this can actually trigger pitting corrosion. Okay, so halide ions were found to be the main factors for pitting corrosion. Pitting corrosion is highly accelerated if chloride, sulfate, or bromide ions are present in the electrolyte solution. Okay. So that is why if you use chlorinated water, I mean our tap water is actually treated with chlorine, so it contains some chloride. Then you know that this can actually trigger pitting corrosion. That is why sometimes when you fix your car and then your radiator tank is actually almost at the low level, don't put tap water. Don't put running water. Running tap water or the city water. The reason why is because city water is a chlorine treated water. Then it could be harmful to your radiator or to the metals lining in the radiator. So that is why sometimes they use what? Rainwater. They use rainwater or they use mineral water to be put in the radiator tank. Right, so this is where the formation of pits can be explained. It happens that you have chloride ions from NaCl solution. And this is actually the example if you have a pitting on aluminium. Still the same thing, you have alumina passive layer, and when it fails, it actually can promote pitting corrosion as well. Second type is actually known as crevice corrosion. Okay, so crevice corrosion is actually a consequence of concentration difference of ions or dissolved gas in electrolytic solution proceeds at location covered by the corrosion product and other deposits. Okay, so this is normally happens if you have a joint. Okay, you can see if you have a joint, a pipe joint. Okay, and you actually attach these two joints with a screw or with something, with bolt. And what you can notice over here is that it has a gap. So what happens if you have a gap? This actually can trap dirt or dust or anything like trash or what. So when you have a dirt trapped on this gap or this cavity, it can easily absorb water or moisture to make this region become more humid. So when this area become more wet or more humid, then it can actually make corrosion to the wall. So that is why you see over here the gasket. This is actually the plate lining put in between joints. You can see probably because of it is not being put with like a rubber ring, O-rings or others, then it can probably trap deposits which later on can trigger corrosion. Any questions so far? Right, so this is also another examples of crevice corrosion. The mechanism, you have a cavity, you have a gap that eventually will trap or will absorb all these things. I mean, like oxygen, high oxygen, high pH and low chloride. So that is why I think the corrosion can be easily accelerated. Moving on to the next one, we have galvanic corrosion. Galvanic corrosion can also be categorized as localized corrosion because here in galvanic corrosion, when you have two metals with having different composition or different activity connected together or attached together, it will actually create a galvanic effect, a so-called galvanic effect. And at the same time, if these two metals being treated or being exposed to the same environment, then galvanic corrosion can occur. For example, if you have a screw that is made from maybe from steel attached with the ring that is made from zinc, for example. So you know that zinc will be more reactive when you attach this thing together. Of course, the zinc will be corroded, and this is actually due to the galvanic effect. So what would be the requirement for galvanic corrosion? Of course, the requirement, you should have two different metals with connection, I mean connected, attached, electrically connected, or maybe attached together. And at the same time, you should have the same electrolyte or the same environment. Okay. How you can actually prevent galvanic corrosion is basically putting insulator. When you put an insulator in connection, so what happens is that no galvanic corrosion will be happen, and both materials will retain their physical features. Next one, intergranular corrosion. Intergranular corrosion will happen especially when you have alloys, because as I said, when you have alloys, you will have different phase, and this phase will be separated by grain boundaries. Okay, so grain boundaries is like a border to separate different phase. And because of this, grain boundary is considered as the weak point of, or the weak side of a material, then water and oxygen can easily absorb and making the deposits or the corrosion to likely happen here. Okay, so the driving force of intergranular corrosion is the difference between the electrode potential of the grain boundaries and the grain itself, which form a galvanic cell in presence of electrolyte. The solution of anodic grain starts from the surface and advances along the grain's interface. The process results in deterioration of bonding between the grains and the drop of mechanical properties. Next one, we have selective corrosion. Okay, selective corrosion happens especially for metals that experience anodification. Anodification means that you apply a coating, a metallic coating to the materials. For example, galvanized steel. Galvanized steel, you apply or you actually deep coat steel with zinc. So this process is known as zincification. But selective corrosion is basically a dezincification process where the zinc is actually leached out, okay, to the environment, making the structure become less tough. Then this actually making corrosion to happen anytime. Okay. When one element or constituents of metal is selectively corroded out of a material, it is referred as selective leaching. The most common example is dezincification of brass. And after leaching has occurred, the mechanical properties of the metal are obviously impaired, with some metals that will begin to crack. Okay, so selective coating, as I said, is where you have a leach, a metal leaching of one element from the alloys. And we have finally filiform corrosion. Okay, Filiform corrosion is the surface corrosion where the paint film remains intact, but adhesion to the substrate is destroyed, causing a trail or underfilm corrosion to form. Probably you see this a lot when you see metals being corroded, being applied with paint, and when it corroded, it forms like a gap, like a bubble trapped inside the paint. And this void actually having a high oxygen content or what, then corrosion can occur underneath the paint film. So it is actually different between filiform corrosion and pitting corrosion, because pitting corrosion only happens when you have passive layer, a failure of passive layer. But for filiform corrosion is where the corrosion happens when you have a failure of organic coating, like paint, for example. And filiform corrosion is not a downward propagation as compared to pitting corrosion. It is more like forming a trail, okay, like a worm track, something like that, okay, underneath the organic coating. So I'm not sure whether you've seen a CD player before, a CD driver, CD-ROM. Okay, anyone knows? CD is made from what? Madi, you know what materials actually make CD?
So the normal CD?
CD, yes, the material that produce, the main material, used to produce CD.
I think is polymer.
Polymer? Polymer is actually the coating. You have the metal actually inside the
Metal is
CD.
like aluminium.
Yeah, aluminium. Okay, so for CD or hard disk drive, HDD, both are actually using aluminium. Aluminium is a very good material that it can store information. So this aluminium will be formed into a disk, and it will be coated with plastic. You have a plastic coating, especially for CD. Okay. So have you ever experienced, older CD, CD that you put in the CD player, it cannot work. Probably if it is a song, you see that the song is become like haywire, okay, it has some problems. Okay? The reason why is because there's already been corroded. Okay? So sometimes people, probably you might heard that, okay, don't scratch the CD, because if you scratch the CD, you cannot watch the video or you cannot listen to the song. This is actually true. Why? Because the coating is actually made from plastic, polymer. If you have a scratch, then what happened is that this actually can makes oxygen and water to come in and then corrode the aluminium inside the CD. So sometimes you will notice that it will form like this, a worm-like structure. In older CD, old CD, you will notice this. Then this actually means that it's already forming filiform corrosion. Okay. Any questions so far for localized corrosion before I move to combined effect of corrosion? So far, any question? Yes, no? All right. The combined effect of mechanical factors and corrosion. I've told you that for this type of corrosion, it is basically mechanical effect with electrochemical, have mechanical factors and also corrosion factors. It can be categorized into 4 different parts. You have like stress corrosion, corrosion fatigue, erosion corrosion, and also fretting corrosion. The first one, SCC, stress corrosion cracking. This happens when you have the combined effect of tensile stress with corrosive environment. Okay. And things that you need to remember is that for stress corrosion cracking, the amount of stress applied or the amount of load applied will be static stress. Okay? Meaning that the load will be applied to this material will always going to be constant stress. Okay. All right. So when you have a static stress applied to the material and also corrosion, what happens is that the grain boundaries will start to crack and it will actually form corrosion. Okay. So the cracks induced by stress corrosion may be intergranular, transgranular, or mixed, which means a combination between intergranular and transgranular. Intergranular normally is smaller forms of cracks. Transgranular is a combination of a few intergranular cracks. Then this is what you will get, I mean, for the stress cracking corrosion. Transgranular and the small is actually intergranular cracking. Corrosion fatigue, basically the same concept with stress cracking corrosion, which means you have a tensile applied to the materials and at the same time corrosive environment. But the difference is only that you have a different stress, different amount of stress being applied to the material. Not like stress cracking corrosion where you have a uniform or static tensile. For corrosion fatigue, normally it will be always varying of stress or loading amount. And lastly, we have fretting corrosion. Okay, fretting corrosion is of course a corrosion that is caused by rubbing effect, rubbing or friction effect, caused by rubbing of two contact surface under load, which lead to the steady erosion materials. For example, piston. You can see piston in engine. When the piston move, there's an erosion, there's a rubbing or there's a fretting effect. This actually makes the piston have more tendency to corrode because it's having a rubbing effect, fretting that later on can trigger corrosion fast. Yeah, and another thing will be on erosion corrosion. Erosion corrosion is basically the combination of erosion and corrosion. For example, if you look at this pipe, the design, it has like a sharp turning like this. So when you have any fluid movement, like water, when it goes to this 90-degree angle, what happens is that this will create so-called like a cyclone, and you have like more erosion of water here. Okay, so when you have more erosion and formation of cyclones over here, then corrosion can easily be happen, and this actually can create erosion corrosion. Other than that, cavitation corrosion is caused by attachment of bubbles or gas on the surface. Okay. Cavitation corrosion is erosion caused by the combined effect of corrosion and the pressure caused by the breaking of gas bubble from the liquid. So if you notice, if you put like high velocity of liquids, and then when it goes to another big container, it can easily form bubbles. So when you have bubbles, bubbles will be attached on the walls of the container, and this actually can trigger corrosion because inside the bubble you have gas. Okay, so all this can be actually seen here. It forms like a very rough surface, meaning that this actually previously been attached by bubbles. Hydrogen embrittlement is where you have a trapped gas. Normally, hydrogen gas trapped in the materials. So this can actually create a pressure, okay, to the materials, and later on can degrade the metals. So hydrogen embrittlement, you can see it a lot in batteries. That is why you see that all those times we have Nokia 3310 or other older versions of handphone that is made from or use nickel cadmium batteries. So sometimes you will notice that the older batteries, if it is no longer good, then it will be slightly expand, not yet to explode, but slightly expand. Then this actually indicate that it already undergoes a reduction process and it contains hydrogen gas inside. So that is why you've heard about the news where batteries or power bank will be explode. Reason why is because it has a trapped gas inside, and when this material become like highly pressurized, it can actually degrade the materials, and what happens after degrade? Corrosion and also leaking, and that can actually cause explosion. Internal pressure that generated by the trapped gas can approach 1 megapascal, quite high. I mean, even though it is just hydrogen gas inside the wall, but it can actually develop a very high pressure, which at the same time can be dangerous because you have some like applied or compressed gas inside the wall. Then this actually can be I think dangerous or triggering corrosion. Last but not least, as I said earlier, you have microbiological corrosion. Okay, microbiological corrosion is simply defined as corrosion that is, created or initiated by microorganisms, like for example, bacteria. So if you have like studied biology before, you understand that microbe, for example, Pseudomonas, it has like unfixed structure. It has plenty of legs, okay, and it can actually excrete slime or probably some liquid outside their body. So what happens is that when they attach to a metal surface, okay, this slime is basically probably rich with acid or what to digest the host that they are detached with. And after that, when it is digested, then it will be absorbed to the microbes to be eaten as a source of food. Okay, but in this case, we have like two types of bacteria that normally can trigger corrosion, microbiological corrosion, or MIC, microbiological induced corrosion. Okay, so you have IRB and you have SRB. IRB stands for iron reducing bacteria, and then SRB is sulfate reducing bacteria. So this bacteria actually reduce, like IRB reduce iron, and sulfate, it will actually reduce sulfate into hydrogen sulfate. And hydrogen sulfate, of course, you know that it is very corrosive. Okay, right. So yeah, basically it's like that. And in fact, if you notice that MIC can always happen in pipeline, because a pipeline normally that transport water, they still use metal pipe. And if you cut through, you will see that it can actually form like tubercle, like this. The tubercle is basically the deposits resulted from the reaction between the bacteria and also with the metals. Okay. Right, to summarize different types of corrosion, you can see it, I think, over here. Basically, we have like uniform corrosion, intergranular, and whatnot. So in terms of the driving force, the corrosion, the control point, and what will be the remarks, yeah, maybe you can read up just to differentiate all these methods together. Right. Any question for types of corrosion before we move on to corrosion controls method? Anything? All right.
Doctor, I have a question.
Yes.
Let's say for the localized corrosion, Is it possible for the corrosion to happen in combination, like the intergranular will occur along with a selective?
Okay,
Is it
understood. I
possible?
get what you mean. In a corrosion process, sometimes it can be a combination of all. It's not basically meaning that one materials will undergo a very specific types of corrosion. It can be a combination as well. Of course, it depends on the environment and also the types of materials or metals that we are dealing with. So sometimes you can see that that material will experience like pitting corrosion. At the same time, it can also experience stress cracking corrosion if, let's say, it has been like applied to to some mechanical effect or what. So to me, as I said, the types of corrosion is just a type. To categorize the process that happened, but in reality, some materials may experience more than one type of corrosion. So the answer is yes.
Okay,
Right?
thank you, Doctor.
All right. Any other question? Okay, so we move on to corrosion controls method. As I said to you earlier in this chapter, we have 5 major methods to control corrosion. Controlling corrosion, it doesn't mean to stop immediately the process, but actually to reduce. We want to reduce what? We want to reduce the corrosion rate. This is actually the aim of corrosion control. Reduce corrosion rate. Because I think to stop corrosion definitely is not really possible, because you still have another effect that can trigger corrosion. But at least if we reduce the corrosion rate or reduce the corrosivity, then this actually will prolong the lifespan of the material or our budget. So we have 5 major methods to control corrosion. First one is known as material selection. Second one, by modifying the environment. Third, by protective coating. Fourth, by imposing electric current. And fifth, by a proper design. So we are going to discuss this one by one. Right. So controlling corrosion actually involves hindering the natural chemical reactions that occurs between the metal and its environment. So the common methods used as what we have said earlier, these 5 different methods. And the first one basically on material selection. When you want to produce a material, for example, like alloys, always remember that material selection is one of the priority, because it depends on the environment that you are working with. You will suggest what would be the best element to be integrated or to be added into your alloys, right? The corrosion of metal in surface environment are depending on the types of metal and also the chemical composition of metals. So that is why every metal has its own special composition and special different grades. Like aluminum alloy AA6061, you have also stainless steel SS304, SS306, 316, 318, all actually having different grades because it has a different element composition. If let's say that you want to work with marine environment, you know that if you are going to work with pure iron, it is not suitable because it can actually trigger corrosion and the materials will be damaged fast. But how about if you use copper, because you know copper is slightly corrosion resistant, then this is actually a good material. Of course, if you have alloys like copper with zinc alloy, it is much more better. And in fact, if you use a more corrosion resistant materials like titanium, this is much more better. That is why I think you see a lot of materials these days, they use titanium, like bicycle, badminton racket, or what, they use titanium because the advantages of titanium is that not only it is corrosion resistant, but it is also light in weight, very light. Another thing is if you work at high pressure, then of course you will use stainless steel. The best is if you use a higher grades of stainless steel, because a higher grade actually will prevent the material for any cracks or any corrosion damage, because the layer of passive is basically more durable. If you're working at the damp environment, then of course the most suitable one will be alloys like iron nickel, or the alloys of iron with zinc, but not to use a pure iron, like pure zinc, pure irons or pure metals. Right. So modifying the properties of metals, alloying is also another method, and apart from alloying, passivity or passivation is also another method to passivate the metals. The passive oxide film can inhibit the aqueous corrosion as well. So that is why, as I said earlier, if you have production of alloys or the formation of passive layer due to the incorporation of chromium, which eventually create this chromium zinc oxide layer, this actually will give a barrier or a separation of environment between metals to the electrolyte. Okay. As an example for stainless steel, you will see that the SS304 having around 18% of chromium with 8% of nickel, and for SS316 you have a further addition of around 2% of molybdenum, okay, which also increase the corrosion resistance of that metal. All right, next method is basically on modifying the environment, because the environment that we always talk about when we deal with corrosion is with the presence of water, presence of oxygen, presence of impurities like halides, ions, and many other things. So you can actually control the environment by controlling the environment first. If you want to control the humidity, because if the environment is very humid, then it is not good for metals. Then you can actually have a dehumidifier, because dehumidifier will actually reduce the relative humidity, RH. This actually means relative humidity. Relative humidity. Okay. Right. So if you have less than 50%, then the material that can easily corrode will less likely to corrode. Another thing is, if you want to remove oxygen from electrolyte, then you can actually introduce oxygen scavenger. Okay. Oxygen scavenger. Where's the oxygen scavenger? Okay. So oxygen scavengers actually converts oxygen into other material. For example, if you have hydrazine, this is a hydrazine. The structure is more or less like this. You have N2H4. This is hydrazine. It can easily react with oxygen. Okay, so when it reacts with oxygen, what happens is that it will form nitrogen gas plus with water. So you have no more oxygen, because you know, if you have more oxygen in the environment, this can actually promote oxidation. The objective actually to introduce oxygen scavenger is actually to lower down the oxygen concentration. Okay, right. Apart from that, the environment can also be controlled by controlling pH. Okay, because if you control the pH, if the environment is very acidic, then you have a lot of H+. And when you have lots of H+, then the formation of hydrogen gas will be more fast, then it will be corrosive. Then of course, if you adjust the pH, you will add like base or whatsoever to make it more neutral or more basic. Other than that, other ions contaminant can be removed, because some ionic contaminants, like for example chloride, can actually accelerate corrosion. So that is why some people, they install filtering aid or filtering column to their water supply, so that all the ion contaminants can be eliminated. Secondly, for modifying environment, we can use corrosion inhibitor, or sometimes we call it as CI, corrosion inhibitor, CI. Okay. So corrosion inhibitor is basically my area, during my master's and also my PhD. So I can talk a lot about corrosion inhibitors, but I think what is the most essential things that you should know for corrosion inhibitors? It is basically a chemical compound, okay, that is added in a small concentration to the environment, which eventually reduce the corrosion rate. Okay, chemical compounds added in a small concentration, which eventually reduce the corrosion rate. Okay, right. So for corrosion inhibitors, it has certain criteria to be selected as a good corrosion inhibitors. CI criteria. Okay. So first, of course, types of chemical compound that is used for corrosion inhibitor, it must have electron-rich functionalities. Okay. For example, that it has a heteroatoms. It has nitrogen, oxygen, sulfur. It has pi bond. It also have a lone pair. Okay. So this is actually what makes that chemical compound to be used as a corrosion inhibitors. For example, I give a simple example: phenol. Can someone tell me what will be the features of phenol that I can categorize this as a corrosion inhibitor? Jihan? Based on what I have explained earlier, can you actually relate from the structure of phenol how it can be a good candidate for corrosion inhibitor? Jihan, do you have any ideas?
I think doctor, بس no, don't have any idea.
Okay. Any other things?
I'm so sorry.
It's okay. Shamira, do you have any idea?
Maybe because it has oxygen.
Okay.
On pair, yeah.
Okay, so it has a heteroatom, it has an oxygen over here. And okay, so probably if you look on this structure, you'll notice that it has a lone pair here, isn't it? Okay, meaning that it has a electron-rich region over here. In the same time, in the aromatic ring, you'll see that it has a double bond here. You have like three pi bond. So this 3 pi bond actually indicate that it has a electron rich also, because like 1 or sigma bond actually have like how many electrons bonded? You have 2 electrons, right? If you have a pi bond, then how many electrons been bonded? 4 electrons. So you have like pi bond over here, you have pi bond over here, and pi bond over here. So basically, it tells you that this bonding, it has more electrons. Then when you have a more electrons, then it will be useful for your inhibitors. Okay. So allow me to explain a bit about the role of corrosion inhibitors. Okay. So basically, what you have to understand is that when a metal is being put in the solution, you have a metal, you put in the solution. Okay. Example, this is iron. It will experience corrosion immediately. But if you add corrosion inhibitors, CI, for example, maybe I put example of phenol. You can actually put other types of corrosion inhibitor as long as it fulfills the requirement. Then this actually can reduce the corrosivity of iron. How it works? Okay. So you know that from the first process, okay, Fe will be oxidized to Fe2+. Okay, plus 2 electrons. Okay, you have a metal dissolution. Okay, so basically what happens is that the surface of metals now become like positively charged. Oops. Okay. All right. So imagine that in this solution you have like water. Water, probably you have OH minus, or maybe chloride ions or others. So this, positively charged surface can eventually attract negatively charged ions in the electrolyte. Probably if I put like OH minus, OH minus, okay, OH minus, and OH minus here, because it's like an electrostatic interaction. You have like a so-called migration, remember in first chapter, mass transport. Okay. So if you put the corrosion inhibitor inside the electrolyte, okay, imagine that if you have like electron rich functionalities, this actually can make a so-called retrodonation, because Fe will have like less electron in the d orbitals, because it already removed 2 electrons. Okay? 2 electrons removed from d orbital. Then, if anything that has electron rich, like for example from hydroxyl over here, it can actually form an interaction, okay, between the lone pair and also the d orbitals of Fe. So this actually can create a so-called like a bonding, like a temporary bonding, which actually compete or probably like scavenge or jeopardize the adsorption of OH minus ion onto the surface, because it's already reacted together with the inhibitor. Because you know, once this been formed, it can actually form Fe, okay, OH2, okay, and then this actually already becoming rust. Okay. So when you stop the process at one point, then this actually can reduce the corrosion process. Right. So not only because of this, if you see the pi bond, it is also electron rich. It also have orbitals. It can also be like overlap with the d orbitals and forming like a bond. So not only at one side or one orientation, you can also have other parts of orientation. Okay. And another thing to highlight you is that this interaction is known as chemical adsorption or chemisorption. I believe some of you have taken 504, KAA 507 on adsorption. So you might heard about chemical adsorption because this interaction is actually a chemical bonding. Okay? It forms like a chemical bonding. And this is actually what we call it as chemisorption. For chemisorption, always remember that the delta G values are normally around minus 40 kilojoule per mole or lower. Or lower means that more negative, negative 50, negative 60 or what. Okay? All right. There's also another way that corrosion inhibitors can work. First, as I said, you can have a migration if this process happens too fast. Another thing is in water also there's a H plus that may present in the electrolyte. So H plus can actually react with the inhibitor, any sort of inhibitor. For example, like this case, we use phenol as an example. Okay. So it can react especially with hydroxy because hydroxy is electron rich. It will attack this and it will form a so-called a protonated phenol. OH2 lah. And then this will be positively charged. So remember earlier I told you that once you have like metal dissolution, Fe become Fe2 plus, the surface will be positively charged. It will actually attract negatively charged ion, OH minus or Cl minus, to be absorbed on the surface. This is actually called as migration because we know this is actually the effect of electrostatic interaction. Okay. All right. So the surface now being covered with negatively charged ion. If there is no inhibitor, it will further oxidize and it will form rust. But if you add the inhibitor and if the H plus reacted with phenol, then it will be protonated phenol. Then this actually will give interaction between the positively charged inhibitor with negatively charged surface. Okay? So this actually will form like interaction. So this interaction is temporary and known as physical adsorption or physisorption. Okay. So physisorption happens when you have an electrostatic interaction. Okay. Due to the positive negative interaction. Right? Okay, so with this formation, with whether physical adsorption or chemical adsorption, okay, so it actually can stop or reduce the formation of or the oxidation process of metal to become rust. Okay, and probably you might ask, for one type of inhibitor, are they going to like perform one type of adsorption or it can be both? The answer is actually inhibitor can perform both ways. It can actually forming physical adsorption or chemical adsorption or both together. Okay, so it's the mechanism is always complicated. And before that, I think you should also remember that for physical adsorption, the delta G value should be minus 20 kilojoule per mole or higher. Higher means more positive. Okay? Minus 10, 0, positive 10. Okay. So if if you actually calculate the delta G and you get like -20, then you know that, okay, the inhibition process is basically physical adsorption. All right. So we can actually categorize inhibitor into different types. Anodic inhibitors, cathodic inhibitors, or mixed type inhibitors. What does it mean by anodic inhibitors? Anodic inhibitor, it means that the inhibitor actually inhibit the oxidation process. As I said, okay, for corrosion process, the process that occurs at anode is basically oxidation. So if the inhibitor actually jeopardize the oxidation process, then we call it as anodic inhibitors. Meanwhile, for cathodic inhibitors, we know that at cathode, the process will always going to be reduction process. Okay? So when you add the inhibitor and if it jeopardize the evolution of hydrogen gas or what, then this can be categorized as cathodic inhibitors, right? And if the inhibitor actually jeopardize both process, then we call it as mixed inhibitor. Most of corrosion inhibitors, especially organic corrosion inhibitors, will have mixed inhibition properties. Okay. For anodic, normally a specific like chromate, nitrate, borate, these are actually the examples. For cathodic inhibitors, it can be like zinc salt, magnesium salts, and amine. Okay, so this could be cathodic inhibitors. But for mixed inhibitors, as I said, like normally is for organic inhibitors from plant extract, from synthesized compound or whatsoever. And furthermore, we also have VCI, volatile corrosion inhibitors, that is used in oil and gas, because in some process, it doesn't require like electrolyte, and it is actually in a closed vapor space with gas. So that is why we need to use some volatile compounds like dicyclohexylamine, cyclohexylamine, normally amine, that will be used as a VCI. The function and the process is still the same. Okay. All right. Any questions so far for corrosion inhibitors and material selection? Anything that you want to ask? Okay, so before we end the lecture, actually, just to show you the role of corrosion inhibitors, as I said, once it forms the interaction as it is actually forms adsorption film. It will react with aggressive agent. It will form a passive layer and form adsorption film or protective layer on the metal surface. So you can see, like for example, this one. You have a phosphate. Phosphate reacted with a metal. It forms an interaction. So this actually will create something like a film. Okay. So when you have this formation, of course, there's no further oxidation of iron, then of course the formation of rust could be reduced. Okay, I believe for protective coating, we can continue next week. We still have a few for methods for corrosion protection, but I believe within Tuesday next week we can finish, and even next Tuesday we can start with a new chapter, kinetics of corrosion electrochemistry. So any questions so far? Anything that you want to ask?
Doctor, I just want to clarify.
Okay.
For the corrosion control, let's say we are working with a metal pipe, and then do we perform the corrosion control before we use the pipe in our operation or during the operation?
Okay. Normally it can be like both ways. It can be, applied during the process, or it can be applied before the process. But both the aim is actually the same. We want to reduce the corrosion, because sometimes if the material itself doesn't being exposed to the environment, like for example, if you have a pipe which doesn't been filled with any solution or any corrosive solution, then it's not going to be like experience corrosion. But during the process, probably it can trigger. Then normally we should like apply some methods like maybe cathodic protection or what to control the pipes. So basically, if you ask me, it can work both ways. Normally, as a precaution, because this is actually as a precaution, we can actually, apply corrosion protection methods before the process and also during the process. Okay. And it all depends on the materials and also the types of environment that you're dealing with. Okay. Any other question?
Another thing,
Mm-hmm.
let's say for the metal pipe, we already perform the corrosion control and still corrosion happens. And then I'm sure that we have to replace the metal for our operation, right? And then what we do with the corroded metals, do we just dispose them?
Normally dispose. We can consider it as a metal scrap. But if the corrosion control method is not successful, then meaning that the method used is not suitable. Then if you can find alternative to use other types of corrosion control, then you can try. For example, maybe if you apply cathodic protection, because we have not learned about cathodic protection yet, but in some cases, cathodic protection could be not successful if the environment is too much acidic, too much basic or what. Then it can, cathodic protection cannot happen. Then what happened is that we have to change it into anodic protection and whatsoever. So the selection of controlling methods is essential to determine the best condition that can reduce the corrosion rate. Otherwise, if it is not working, then meaning that the methods that we choose is not suitable. Okay.
Okay, thank you, Doctor.
Welcome. Any other question from the floor? Others?
No, it's clear so far, Doctor.
Okay, so I guess as what I've told you earlier that for today we are going to have a quiz 3. I will upload it right after this, and I will upload also your lecture notes for chapter 4, because next week, I think Tuesday, we are going to start with chapter 4. And yeah, so far, if you guys have any question, you can let me know quickly, and yeah, we can discuss it in the next class. So with that, thank you very much for your kind attention. Hope to see you next week. So have a good weekend, have a good day, and thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thanks, Doctor.
Thank you, Doctor.
Salam. Thank you,
Thank you,
Doctor.
Doctor.
Much.
Yeah, welcome.
Thank you, Doctor.